The previous paper was about the architecture. This one is about techniques to train GANs. The videos are online, so I'm not going to spend too much time on this. I'm going to give you a brief overview, and then you can ask questions if there are any leftover questions. What are the ideas then? What are these techniques? One of the techniques is feature matching, and we are going to see this idea later on in another form. And the idea is that rather than having your discriminator discriminate between generated and fake images, stop at the feature level of a discriminator and compare the features. Mini-batch discrimination. In the previous paper, one of the suggestions was use batch normalization. And the idea is not only look at this example, but look at some other examples in your data set. And perhaps that is going to help you escape mode collapse. And mode collapse is whenever you have a distribution, let's say, with multiple peaks or multiple modes. GANs, if you keep training them, you're going to see that it's going to pick one of the modes during training. So maybe for a couple of iterations, GANs is going to focus on one of the modes, and then it's going to switch to another mode. And this is one of the big problems with training GANs. The idea here is not only look at a single image, look at the images in the neighborhood, not even in the neighborhood, look at some other images, and then use those as features that are going to go inside your discriminator. And this is going to help you deal with the mode collapse. The other idea is historical averaging. Keep a window of your parameters and then average them. And then the average network is the one that you're going to be using. The other one is label smoothing, and it's one-sided label smoothing. You don't want your discriminator to be pulled towards the mistakes of your generator. Set beta to be 0, and alpha, rather than being 1, you can set it to be 0.9 or 0.95, a number close to 1. And the other one is virtual batch normalization. Rather than doing batch normalization and computing the statistics of your mini batch, you're going to be keeping aside a selected set of images on the side, and then compute your statistics based on those. This way, there is going to be less variation, less randomness in your architecture. So these are for the improved techniques. And why am I mentioning these techniques? Because once you sit behind the computer, and let's say you have a project based on GANs, it is not enough to know the usual loss function, and it's not going to converge. And therefore, you need to know all of these details, and you need to try them out. You need to know about feature matching, mini-batch discrimination, perhaps historical averaging is going to help you. You need to know a lot of tricks to make them work. But the main reason I'm covering this paper is because of Inception Score. Prior to this paper, people were judging the quality of different architectures or different generators by asking human beings, is this image realistic looking? Yes or no? Is the image coming out of this architecture better than the other image? Yes or no? And they were showing it to human beings. Here, this is brilliant. You are going to use a pre-trained network to give you a score to compare different generated images. Not only GANs is using a different network, perhaps a discriminator, to write down its loss function. To judge the quality of the generated images, you are going to use another neural network. And what is this neural network doing? This is just a classifier. It is trained on ImageNet. It is the Inception architecture from Google. What you do is you keep showing it generated images. That architecture is going to classify them. And what you want out of your labels that are coming out of this classifier, you want them to be as diverse as possible. So you want your distribution to have a high entropy. Why is that? Because you want to see a diverse set of images being generated. Cats, dogs, airplanes, fish, etc. At the same time, if you focus on a particular class, you want your distribution to be narrow, to have low entropy. And this is a sense of high quality images for that class. And if you keep those two objective functions in mind, add them up, that's going to give you KL divergence. but then you want that over all of your data or over all of the generated images. Any questions so far about Inception Score or any other list of improved techniques here? Okay, awesome. In the previous paper, we saw an application of generative adversarial neural network framework, and that was unsupervised learning. You look at the features that are coming out of your discriminator, and those features are going to be the features that you're going to be using in some downstream task, and they are learned in an unsupervised fashion. But what if you have a semi-supervised learning framework where you have a large data set of unsupervised data without any label? So these are unlabeled data. And then you have a small supplementary data set of labeled images or labeled data. That is called semi-supervised learning. You can actually use GANs to do semi-supervised learning as well. What are you going to do? You're going to have a generator that's going to keep generating data. What we want from that generator is to generate images that look like realistic images. So the generator's job is clear. You're going to have in your data set, some of your data are going to have labels. And let's say you have K capital labels. And then some data are going to end up being unlabeled. The ones that are unlabeled, you're going to put them in the last class. So that's going to be K plus 1 class. Now you want to have a discriminator to be able not only to train your generator, but at the same time to be good at classification. And that's all we are writing here. You want your discriminator to not only classify between these classes or K plus 1 classes, but at the same time use it to train your generator. I think if there is time later on, right after going through GANs, we are going to focus for a little while on semi-supervised learning and self-supervised learning and unsupervised learning. And then you are going to see more methodologies. So GANs is not the only solution to semi-supervised learning. Any questions about semi-supervised learning using GANs? The video is online. Make sure that you watch that because we spent a lot of time going through the math in that video. Any questions? Was everything clear? Okay, perfect.